Section 9.6, Multiple Bonds. In this section, we are going to expand upon what we've learned about bond overlap. And we know that there are two different ways that orbitals can overlap to form bonds between atoms. One of them is called sigma bonds, and the other one is called pi bonds. We'll start with sigma. Now this symbol is the lowercase Greek letter for sigma. You guys are used to the uppercase sigma for summation. This is the lowercase sigma. Kind of looks like an O with a little tail. Sigma bonds are characterized by direct end-to-end overlap. And so the images we were looking at previously in this chapter showed sigma bonds, where you envision these two electron clouds essentially colliding or overlapping, intersecting, and that's where the bond will form. So you can have this with two s orbitals, and wherever they overlap in that region, that would be your sigma bond. You can have it with an s and a p orbital, and again, there's your overlap region. That's a sigma bond. Or a third possible way is to have two p orbitals overlap to also form a sigma bond. Now we know that these sigma bonds are stronger than pi bonds just because there's a greater amount of overlap. And one thing that's common to all three of these examples of bonds is that the electron density lies on an axis between the nuclei. So here's the two nuclei, and of course that line that connects them, there's your electron density. Same thing with the s and p overlap. Here's your nucleus, and there's again your electron density. So that bond is formed when the electrons clouds overlap between the two nuclei. Pi bonds, on the other hand, pi bonds are characterized by side-to-side overlap. And so in order to have a pi bond, we notice that we have two regions of electron density, both one above and below the plane of the nuclei. So it's very different. It's not between the two nuclei itself, but instead above and below the plane of where those two nuclei are connected. And notice there's no s orbital shown anywhere here, and so to make a pi bond, unhybridized p orbitals are required. How do we recognize in a compound if bonds are sigma or pi bonds? Sigma bonds are always going to be single bonds are always going to be the sigma bonds, and I always remember that single and sigma both start with s. So if you have this diatomic hydrogen, that's just a single bond by itself, that will be a sigma bond. In a multiple bond, meaning either a double or a triple, one of the bonds will be a sigma bond, and then whatever many bonds the rest of them are, or however many additional bonds there are, those would be classified as pi bonds. So in this double bond, we see that there's one sigma and then one pi. And in a triple bond, like in the case of diatomic nitrogen, there would be one sigma and two pi's. Now we have no way of knowing which one is the sigma and which one is the pi in this type of representation where there's just three lines, but we do know that one has to be a sigma bond and the other two are pi. Let's take a look at an example, and I have ethylene here, C2H2, H4, and the first question we're going to ask is how many sigma and how many pi bonds are there? And I think the easiest way is to go through and just label them. And so right away I see these single bonds, which I would label as sigmas. So right away I see 4 single bonds or 4 sigmas. And then in the double bond in the middle, there's one sigma, and then the other one would be classified as a pi bond. So in ethylene, there's 5 sigma bonds and 1 pi bond. What is the hybridization of each carbon? Well, each carbon has 1, 2, 3 areas of electron density around it, or 3 electron domains. So we talked about hybridization last week. That would be sp2 hybrid. How many hybrid orbitals are there? One of the things we talked about in section 9.5 is however many orbitals you use to form the hybrid orbitals, you have to start and end with the same number. So s plus 2 p orbitals would be a total of 3 hybrid orbitals. How many unhybridized p orbitals would be left? If you think about the formation of an sp2 hybrid, it's going to use up 1 s and 2 p orbitals. That leaves this single p, unhybridized p orbital left. So there's one that is not included in that hybridization. Now, what does it look like? If we take a look at take a step back and look at a big picture of how this molecule looks like, we have classified it to have 5 sigma bonds and 1 pi bond. And so if we take a look at this drawing, the overlap regions here's 1 sigma bond, here's another, here's a third, and a fourth, and then one in the middle is 5. So those are your 5 sigma bonds formed when those orbitals simply overlap. So those represent the singles between carbon and hydrogen, and one of the bonds between the 2 carbons. The last bond, the pi bond, is going to be formed by the side-to-side overlap between these 2 p orbitals. Now you can see they naturally don't intersect. That amount of overlap isn't there automatically, which kind of helps explain why pi bonds are a little bit weaker than sigma bonds. And again, here's your plane of the nuclei, and we see that that pi bond is formed both above and below the plane of those nuclei. Let's take a look at one more example. Acetylene, C2H2, and we're going to kind of go through the same process. So first question, how many sigma and pi bonds does it have? Here we have 1 sigma, a second sigma, and in that triple bond we know that 1 is sigma and the other 2 would be classified as pi. And so in acetylene we would have 3 sigmas and 2 pi bonds. What's the hybridization of each carbon? Now they happen to be the same because it's a symmetrical molecule. We have 1, 2 areas of electron density, and so the number of electron domains would be 2. So our hybridization would be sp. How many hybrid orbitals, how many sp hybrid orbitals are there? Again, if we take a look at how that hybrid forms, if we need 2 electron domains, I need 2 hybrid orbitals. So if I put together 1 s and 1 p, that's going to be 2 hybrid orbitals, leaving 1, 2 unhybridized p orbitals. And lastly, what does it look like? Let's take a look at an image again here. And we counted up 3 sigmas and 2 pi bonds. So an overlap between the sp hybrid orbital on carbon and then the s orbital on hydrogen, that's going to be 1 sigma bond. Same thing on the other side. And then the overlap of the sp on 1 carbon and the sp on the second carbon, that's going to be your 3rd sigma bond. And already labeled in the drawing, we have 2 pi bonds, both formed using regular old unhybridized p orbitals. And you can see that the first one is kind of above and below the plane of the nuclei. And then the other one we envision as being in front of the screen and behind the screen for that second p orbital overlap to form that pi bond. Now the last slide, we're going to have you pause the video for a minute and determine the number of sigma and pi bonds present in the following structures. So take a minute to pause the video and have everybody count them up, and when you're ready, you can start up the video again. All right, hopefully you've had a chance to label everything. On this left structure, sigma bonds are, again, all the singles and one of the multiple bonds, and the other bonds in the multiple would be pi bonds. So in terms of sigmas, 1, 2, 3, 4, 5, 6, and pi bonds would be 2. And on the other structure, I'll count the sigmas first. And we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds. And pi bonds would be 1, 2. And that brings us to an end of Chapter 9.